Hi, this is Zhilei Ren from Dalian University of Technology, China. It is a great honor to have such opportunity to present our work, Automated Patching for Unreproducible Builds. First, the background. This study is about reproducible builds. A software build is reproducible if given the same source code, build environment, and build instructions. End user can generate bit-by-bit identical copies of all specified artifacts. Due to its applications to build environment safety, software debugging, and continuous delivery, various software repositories have initiated their reproducibility check, such as Debian, Geeks, and Arch Linux. The reproducibility validation workflow is as follows. Given the source files of a package, the build process is conducted under controlled, altered build environments. Factors such as build date, locales, file system metadata are perturbed to check whether identical artifacts could be built. If so, the build is called reproducible. Otherwise, developers would locate the problematic file and fix the issue accordingly. Unfortunately, currently, the fixing process is mainly manually conducted. Towards the automated fixing of such issues, we have identified two major challenges. First, the localization granularity challenge. Although there have been automated localization approaches, the localization results could be only realized at file level, which is not sufficient for the fixing process. Second, the historical knowledge utilization challenge. For software distributions like Debian, various patches for fixing the unreproducible build issues have been accumulated. However, how to leverage the historical knowledge to fix new packages remains a great challenge. Here is a motivating example. On the left, we present a snippet of diff log, which indicates an inconsistent file between two builds. The file is a Perl script, in which there is a timestamp. When the build process is carried out at different time, this file will be different, making the build process unreproducible. To fix this issue, we have to first locate the problematic file, as shown in the right figure. Moreover, we have to obtain fine-grained location info, that is, the date command invoked in line 42. Then, we have to generate a patch to fix such issue. For Debian, an environment variable specification source date epoch has been proposed for timestamp related issues. For example, Debian Package Manager assigns this variable with the last modification time of the changelog file. There are also related patches solving similar issues with the patches available in Debian's bug tracking system. Therefore, it would be ideal if we could leverage such knowledge for solving issues of other packages. Hence, we propose a novel approach for automatically generating patches for unreproducible builds. On the one hand, to tackle the localization granularity challenge, we design a tracing-based approach, which features a system-level tracing framework to capture the runtime information from both the kernel and the user space applications. On the other hand, to tackle the historical knowledge utilization challenge, we develop a history-based patch generation procedure. By combining the two components, we are able to generate patches for validation. We shall proceed to introduce the framework, which we call repfix. There are two components in repfix: the tracing-based fine-grained localization and the history-based patch generation. We start with the normal build process, which runs in user space. To capture more verbose information such as system calls and function calls, we consider a trace monitor to retrieve this. The trace monitor loads the tracing script and compiles it into the kernel module, which further attaches probes to both the kernel and the user space applications. Under such setup, when the build process initiates, we could obtain not only the build artifacts, but also the build trace. With this as input, we are able to conduct the localization procedure in search of accurate locations of the problematic build commands. With the localization results, the history-based patch generation works as follows. On the one hand, we extract the commands for patching with the command extraction procedure. On the other hand, we retrieve the most similar patch from the existing patches from Debian's bug tracking system. Then, we intend to apply the edit operations of the matched template to the command for patching to obtain the patched command. Afterwards, we generate candidate patches, which are fed to the patch validation procedure for checking to output the patch result. More specifically, we introduce workflow of the two components. First, the localization. We present the build process and the kernel. In particular, we are interested in a set of application functions and system calls. We could attach probes to these functions. When the build process starts, we could capture the traces from both the kernel and the user space applications, which are indicated as utrace and ktrace respectively. With utrace, we could inspect the mapping from the executed build command to their invocation location. Meanwhile, with ktrace, we could obtain the system call information, such as read, write, exeve, etc. Then, we could conduct root cause localization with the ktrace to obtain the problematic build commands that are responsible for the unreproducible builds. Finally, we could curate their fine-grained location from the mapping generated from the utrace. After introducing the localization component, we discuss how the patches are generated. Here, we present an example of patch template. We transfer the command into tokens and obtain the edit operation from the source to the destination. Then, given the command for patching, we could apply the edit operations and transfer the modified tokens back to the candidate patch, which is used for patch validation. In this study, we consider the following validation criteria. First, no artifacts are missing. Second, bit for bit identical artifacts are generated between the two rounds of build. Besides, manual check is also necessary. For example, here we present a malformed patch. In this patch, both the criteria could be met, yet the patch is not valid. For the third part, we present the experimental results. To evaluate the proposed framework, we consider three approaches for comparison. First, repfix proposed in this study. Log test is a localization variant in which we retrieve the line with the highest similarity score with a problematic build command. Repfix text is a variant for repfix, in which the patch generation does not tokenize the commands. Instead, we directly consider text-based edit operation for patching. For the implementation details, in this study, we consider 116 packages from Debian. The patches are also from Debian's backtracking system. Repfix is implemented in Python and Java. For the tracing utility, we'll consider systemtap. In this study, we consider the following 4 research questions. First, is repfix effective in fixing unreproducible builds for real-world packages? Second, how effectively can the tracing-based localization and the history-based patch generation improve the overall solution quality? Third, how efficient is each component of repfix? And fourth, is repfix able to be applied to other unreproducible build packages that have never been solved before? This is the result of RQ1. In the upper figure, we illustrate the statistics of the packages. The number of files ranges from less than 100 to over 2,000, with an average number of around 140. The large number of files poses great challenges for the localization task. We also present the proportions of the reasons for unreproducible builds. We could observe that the majority of the issues are timestamp related, such as the timestamp in compressed files and the embedded output of the date command. In the right figure, we can see that for 64 out of 116 packages, repfix is able to at least fix one issue that is responsible for the unreproducible builds. Hence, we can say that repfix is effective in solving unreproducible build issues. In RQ2, we are interested in the contributions of each component. In the table and the left figure, we compare the localization of repfix with a text similarity-based approach. From the result, it is obvious that repfix outperforms the comparative approach. Meanwhile, if we replace the patch generation of repfix from token-based to text-based, repfix text could only fix issues of 54 packages. By this RQ, we confirm the effectiveness of both the localization and the patch generation. In RQ3, we investigate the time distribution of each component. From the figure, we could observe that the validation is the most time-consuming step, with an average value of around 360 seconds. Also, we compare the build time with and without tracing. We can see that In RQ3, we are interested in the time distribution of each component. From the figure, we could observe that the validation is the most time-consuming step, with an average value of around 360 seconds. Also, we compare the build time with and without tracing. We can see that in RQ3, we investigate the time distribution of each component. From the figure, we can see that the validation is the most time-consuming step, with an average value of around 360 seconds. Also, we compare the build time with and without tracing. We can see that the overhead of the tracing is non-negligible, but in general acceptable. In RQ4, we are interested in applying repfix over new unreproducible packages. we test repfix over a set of Arch Linux packages. In total, repfix is able to resolve the unreproducible issues for 4 packages. We submitted the patches to Arch Linux bug tracking system. All the bug reports have been assigned, and 2 of them have been accepted. Here, we present an example of a submitted patch. The patch was not immediately accepted. Instead, the maintainer suggested reporting the patch upstream. Following the suggestion, we opened an issue at packages repository at GitHub. Also, we explained to the author why the patch should be applied. Finally, the patch was accepted, which was then pushed to Arch Linux repository later, and the bug report was closed. Finally, the conclusion. To the best of our knowledge, this is the first study to generate patches for unreproducible builds in an automated paradigm. The proposed framework features a tracing-based fine-grained localization and history-based patch generation. We also conduct extensive experiments to demonstrate usefulness of repfix. For future directions, we are interested in generating fixing rules from existing patches that solve unreproducible builds. Also, extending the fixing technique to more software repository is an interesting direction. Thank you for watching this video.